Okay, this is a video about limit laws and piecewise function limits. So let's go over the limit laws first and limit theorems. So in these laws, k is a constant. A constant in math just means a number, right? So it's 2, 3, pi, these are all constants. And the other thing we want to say before we read the laws is that we are assuming that the limit of f of x as x approaches a exists and the limit of g of x as x approaches a exists. So these two limits exist, and now we're going to talk about how we can combine them with the limit laws. So first of all, the limit of a constant is a constant. So in other words, if you're saying the limit of the constant function 5 as x approaches 1, well, that's just 5, right? Think of this right here. We're used to thinking of a constant as a number, but in this limit law, you want to think of the constant as a function, right? So when we say this here, the 5 is like a constant function, and then we're saying if you're approaching 1 for your x value, well, your y value is just pegged at the constant. Okay, then we have the limit of, actually, I'm going to go down this way, for the laws. So let's do C now. The limit of the function x as x approaches a is equal to x. What that means is, this function is just the identity function, which is the function y is equal to x, right? So if you're looking at this function at any place, a, right? So the arrow number is a. That means x is equal to a, but that also means at that particular arrow number, y is also equal to a. So we're really at the point a, and the law says that if you approach this x value from either side, well, then the y value also approaches the same thing, right? So the limit of the function is whatever the x value is. Let's see, we've got then the constant multiple law. So that one says that if you had, for example, the limit of 5x squared as x approaches 2, you can pull this constant number out front. This will be 5 times the limit of x squared as x approaches 2. That's what the constant multiple law is. The sum and difference laws say that if you remember, we did say at the beginning that each of these individual limits exists. So if you're combining two functions and the individual limits at the arrow number exist, then we say the limit of the sum, here's the sum, right, is the sum of the limits. So we've got the two individual limits, right, limit 1 and limit 2, and the limit of the sum is the sum of the limits. Also, the limit of the difference is the difference of the limits. Okay, the limit of the product is the product of the limits. The limit of the quotient is the quotient of the limits, but only if the denominator limit is not equal to 0. And then last we have the power law, which says that the limit of a function raised to a power, you can do the limit first and then raise that to the power. And that will become clearer when we do a couple of examples. Okay, so let's apply these laws. So this first one, example 1a, the limit of 7 as x approaches 3. Remember 7, you're thinking of this as a function here, a flat function, a line at y is equal to 7, right? So if you're looking at that and the arrow number is approaching 3, well, the y value is always pegged at 7. The limit of a constant is itself. Same thing here. This is another constant. Same thing here. These laws work for one-sided limits as well. So I'm applying the constant law for all of these. Now, pi is a constant. If you're thinking of that as a function, it's a line at y is equal to pi, right? So wherever your x might be, it doesn't matter. Your y is pegged at pi. This is, again, this is a constant. It doesn't matter where we're approaching. The answer is going to be pi. So all of these right here are the constant law. E is a constant. E is a constant, which is approximately 2.71. If you want to think of it as a graph, it's a function like this at y is equal to e, just a flat line. So if you're at x is equal to pi, which is roughly 3.14, well, y is always just pegged at e, right? So the limit is e. Now here we're using the identity law, the limit of x as x approaches 4. Well, you can also just do direct substitution. Plug the arrow number in there and you get 4 for the identity law. Here we're going to plug the arrow number in and we get pi. Here we're going to plug it in and we get e. Here, remember, one-sided limits, the same laws apply. So the limit of x as x approaches -1 from the left is just -1. Okay, let's see what else. Moving on now to example 2. Okay, example 2 is just doing the same thing, but with the graph. So if you see something like this, the limit of f plus 5g as x approaches -2, well, really what we're saying is if you did the laws, we can break this up into it's a sum. So the limit of the sum is the sum of the limits. So my first step can be this. And then I can use the constant multiple law, right? And I can pull this 5 out here. So I can just do the limit of f as x approaches -2 plus 5 times the limit of g as x approaches -2 to get my answer. And then I go on to the graph to get the numbers, right? Actually, we should check because remember the laws work only if each individual limit exists. So let's check the limit of f as x approaches -2. Here's -2, so as x approaches -2, the limit of f is 1, and the limit of g individually is going to be -1, right? So both of those exist, and so I'm allowed to apply the law, and I'll get 1 plus 5 times -1, which makes -4. Okay. The next one is going to be a product law. So now we're approaching x is approaching 1. The arrow number is 1. So let's check here. If I look at x is equal to 1, I can see that the limit of f as x approaches 1 is 2. But notice that the limit of g does not exist as x approaches 1, right? Because the two-sided limits are not the same. So in a case like this, I'm going to have to do one-sided limits, right? I'm going to have to apply the law in a one-sided way and see what happens, right? So the limit of fg as x approaches 1 from the left is going to be the limit of f as x approaches 1 from the left times the limit of g as x approaches 1 from the left. And let's see what that works out to. The limit of f as x approaches 1 is from the left or the right is 2. And then the limit of g as x approaches 1 from the left, g approaches -2. So it's 2 times -2 or -4. And then if I do the same thing from the right, so if I did the limit of f as x approaches 1 from the right times the limit of g as x approaches 1 from the right, I would get 2. That's the limit of f as x approaches 1 from the right times -1, right, which is -2. So these two do not match up, and so that means that my overall limit is a DNE. This is a DNE. Okay, quotient, well, let's check. Again, we want each of the individual limits to exist. So the limit of f as x approaches 3. Oh, let's extend this graph. This is a bit of a typo, right? So this is 3 here, and the limit of f as x approaches 3 looks like it's equal to 0. And the limit of g as x approaches 3 is equal to 1, okay? So because, again, here's my arrow number. I'm approaching from either side, and g is approaching 1. Okay, so this is equal to 1. So I'm allowed to use the law because A, each of the individual limits exist, and B, the denominator limit is not 0, right? So this answer right here is going to be equal to 0 divided by 1 or 0. Okay, let's do the reverse. Now you notice if I'm doing g divided by f as x approaches 3, because the denominator limit is 0, I'm not allowed to use the law, right? So I have to just think about this differently. And we can think our way through this and say, well, the top is the limit of the top here, which is the g function. As x approaches 3, we can see that g is always approaching 1. The bottom, if x is approaching 3 from the left side, right, then I have a small positive number. And then if x is approaching 3 from the right side, I have a small negative number. So actually, let me write this a little more clearly. I can do one-sided analysis here. I'm really not using the laws because I'm not allowed to, because the denominator limit is 0. But I'm just thinking through this, and I'm saying if x approaches 3, let's do actually the left side first. If x approaches 3 from the left, right, then g is approaching 1, and f is a smaller and smaller positive number. So this is going to become infinity, right, the quotient. If I do the same thing from the right, then f is approaching, g is still approaching 1 from the right as well, right, if I'm coming from this side. F, on the other hand, is a small negative number. So this will be blowing up into a negative infinity. And so overall, this quotient limit will not exist, right? So we're going to talk more about this kind of vertical asymptote situation and infinite limits in the next lesson, or maybe 2 lessons from now. But your takeaways right now are that, first of all, we couldn't just straight apply the quotient law because the denominator is 0, the denominator limit, and we had to think through it using the one-sided limits and looking at what was happening from each side. Okay, moving on to example 3. So example 2 is graphical. Example 3, you're being given the limits, individual limits, right? And you're just being asked to combine them. So it's fairly straightforward. You're using the laws, right? So if you want to practice good math notation, then you can certainly do that, though I won't oblige you to. But if you're looking at this, the limit of f plus 2g, what we're really saying is this is equal to the limit of f as x approaches a plus 2 times the limit of g as x approaches a, right? And we know that this has been given to us as 2, the limit of f as x approaches a is equal to 2. So that's 2. And the limit of g as x approaches a has been given to us as negative 4. So 2 plus negative 8 makes negative 6. Okay, the next one, same idea. I'm going to go quicker. So I'm going to do the notation step in my head and say, well, I can break this up, and I'm going to get 0 for the first piece, and then negative 3 times negative 4 for the second piece. And then the last piece is the limit of 1 as x approaches a. Well, there we're going to use the constant law. The limit of a constant is itself, right? And so I'm going to get 12 plus 1, or 13. Okay, let's take a look at the product. Well, that will just be 2 times negative 4, or negative 8. Okay, here we have the limit of a power, right? So what we're doing in this case is really we're doing the limit of g as x approaches a, and then squaring that, right? And in this case, that would be negative 4 squared, which is positive 16. Same thing here. This is 6 plus f of x to the power 1/3, right? So we can do the limit as x approaches a of 6 plus f of x, and then take that whole thing to the 1/3 power. And to do that, I'm going to get a limit of a constant plus 2, and I'm basically taking that to the 1/3 power. That means 8 to the 1/3, or the cube root of 8, that's equal to 2. Let's see this last one here. The top is going to be 2, and the bottom is going to be negative 4, and so my answer is going to be negative 1/2. Okay, so we have learned to use these laws, which were on the last page, and we need to be able to use them in different ways with graphs, or if we're given the individual limits. And also if we're given equations, and we'll do a lot of that in the next class. Okay, the second part of our lesson today is on piecewise functions. So piecewise functions are interesting to us in limits because they create discontinuities, right? You know, a typical piecewise function, you know, it does one thing for part of the domain and then another thing for another part of the domain and then maybe a third thing for the rest of the domain, right? So a piecewise function is made up of different pieces, which means we have different rules, different equations, right, for each of the subdomains. We call it like here's one subdomain, and then here's another subdomain, and then here's the last subdomain. And in each of those, we have a different equation, okay? So that's just a quick memory jog of what a piecewise function is. And you can see that what happens here is you can create a bunch of breaks, right? Here's a break, and here's a break. And we call these x values where those happen, we call those breakpoints, right? And at the breakpoints is where there's a lot of interesting limit questions, right? Because the limits from the two sides are different. So that's why we spend time on these functions. And direct substitution does not work at the transition values or the breakpoints of piecewise functions, right? So limits at these breakpoints are going to be calculated using one-sided limits, okay? Okay, so here's a piecewise function right here, and let's take a look at what the questions say by sketching this piecewise function, right? So this function is equal to 1 plus x if x is less than -1, x squared if x is between -1 and 1, and 2 minus x if x is greater than 1. So x squared if we're between, let's see, 2 minus equal to sign on this, right? Because we can't necessarily have that in two places. Okay, so we have a number of different things to answer, but the first thing we need to do, I should have actually put this in the words, but I didn't. Let's make a little sketch. I'm going to go off to the side here. So if x is less than -1, then I had the function was 1 plus x, right? So 1 plus x is a line of slope 1, intercept 1, and so this is true for x is less than -1, so it's basically only going to be true here. The second piece was -1 and 1, and by the way, since this is a less than sign, I would put an open circle here. Between -1 and 1, I have x squared, right? So I have a little parabola, right? And it had the equation was written like this, right? So because of these greater than and equal to signs, it's a closed circle here and a closed circle here and a little parabola in between, right? And then the last part is the equation x if x is greater than or equal to 1. Actually, I want to change that. Let's drop that. If I'm greater than 1, then 2 minus x. Well, it turns out it actually does line up like that. It's a line of intercept 2 and slope -1. So it's going to look like this, right? So here is my graph, and now I have to answer. So you need to be able to do that. You need to be able to sketch a quick, simple piecewise function like that. And then you need to be able to look at the limits, right? So here we are looking at the limit of f of x as x approaches 1. That's the first question. As x approaches 1, you can see that the graph approaches 1 from both sides, right? So this is equal to 1. Now, you can also check that from the equation, right? You can put in x is equal to 1. Here is the breakpoint for x is equal to 1, right? These are the two functions on the two sides of 1. So you can put in 1 into both of those functions and see what you get, right? So we could even write it that way. So the limit of f as x approaches 1 from the left, you would use the parabola equation, right? And you would put 1. Don't have to worry about the minus sign there. Just put the number 1 into the parabola equation, you get 1. And then if you put in the x approaching 1 from the plus side, then you have this 2 minus x equation, and you put 2 minus 1 and you get 1, right? So you could do it that way as well, algebraically, and both ways, graphically or algebraically, the answer is 1. Look at negative 1. You can see from the graph clearly that as x approaches 1 from the left side, y is approaching 0. As x approaches 1 from the right side, we'll do that in red, y is approaching 1, right? So the two-sided limits are not the same, and clearly we already know there's a break in the function, a jump there, right? So the overall limit at a jump is a DNE, okay? And so you can also get to that again from the equations, right? You can look at negative 1, and that means we're working with these two equations here. For x less than negative 1, I'll do that in blue. You would say the limit of x as x approaches negative 1 from the left, right? That's the less than side. You're going to put in negative 1 into this equation and get 0. If you're looking at the red side, which means x is greater than negative 1, you're approaching negative 1 from numbers that are greater from the right side, then you're going to put in negative 1 into the parabola equation, and you're going to get 1, right? So you're going to see that the two-sided limits are different, and so the overall limit doesn't exist. So you got to be able to do this with the equation or with the graph. I think I already did these one-sided limits for 1, and you can see that down here. We talked about that already. Okay, so be able to sketch a graph, be able to get the limits from the graph. Let's do one more where you're given a piecewise function and you are looking at the one-sided limits. The breakpoint, right, of the piecewise function here is at 0. So if x is approaching 0 from the right, that would be this piece. If x is approaching 0 from the left, that would be that piece, right? So the limit of f of x as x approaches 0 from the right, you put 0 into the e to the x, and you get e to the 0, which is 1. For this guy approaching from the left, it's a constant, right? So we know from the constant law that that's just going to be 1, and overall this limit is a DNE. Okay, now let's talk about the limit laws as applied to piecewise functions. So when we're applying the limit laws to piecewise functions, we pretty much have to do one-sided limits if you are at the breakpoint, right? So here, the breakpoint for this function is at x is equal to 0, right? No, I'm sorry, at x is equal to negative 1, right? So actually that's why I put this first question here, limit of f plus g as x approaches 0. So if you're looking at f, which is this one, and g, which is this one, right? The breakpoint is at negative 1. So if you're talking about a place that's not the breakpoint as your arrow number, right? You're talking about x is equal to 0, then you don't have to do one-sided limits. You can see that the limit of f as x approaches 0 is equal to negative 1, right? And the limit of g as x approaches 0 is equal to positive 1, right? So you don't have to do any one-sided limits. I'm sorry, I miswrote that. It's positive 1, right? So just add those two with the limit law, and this first answer will be negative 1 plus 1, which is 0, right? What if you have an approach toward the actual breakpoint, right? So the breakpoint here, I want this to be negative 1. I'm sorry. I was trying to approach the breakpoint. So we want x to be approaching, arrow number has to be negative 1 because I want to show you how that works. So if you're approaching negative 1, right, then you have to do one-sided limits because the overall limit law doesn't work because the limit of f as x approaches 1 doesn't exist, and neither does g, right? So we got to do one-sided. So we do limit of f as x approaches negative 1, or we could do it this way. We can say this as x approaches negative 1 from the left. This is equal to the limit of f as x approaches 1 from the left plus the limit of g as x approaches negative 1 from the left. And those two will be, from the left, it's going to be 1 and negative 1, right? So this answer will be 0, okay? And from the right, I'll do that in blue. If you're approaching from the right of f plus g, then we have to do the limit of f as x approaches 1 from the right plus the limit of g as x approaches -1 from the right. So approaching -1 from the right here, remember the whole doesn't matter. The answer here is -1 for f, and for g it's equal to 1, right? And so again, the combined answer is 0, right? Which means that this overall limit here that we started trying to calculate actually does exist. It's going to be 0 because we are approaching from the left and the right and both came out to be 0. But you do have to do a one-sided analysis to get the answer. Let's talk about the next one. The next one is FG, right? FG, again, we want to do a one-sided analysis. So we're going to come in from the left on FG, and that's really the left on F times the left on G. And you're going to get an answer of 1 times -1 or -1. And then you're going to do the same thing from the right on FG, means the right on F, the right of -1 on F times the right of -1 on G. And we're going to get from the right, it was -1 times 1 or -1, right? So overall, again, this does work out and it does exist, but you have to check the one-sided limits if you're working with a piecewise function. Okay, last example is, again, pause the video and see if you can figure these out. It's much of the same that we just did in example 6. Okay, so for all of these, we're going to have to do one-sided limits because at -2, we've got a break for both the functions, and at 1 as well, we have a break for both of the, well, at least for one of the functions, okay? So let's start with the -2 and see what we get for that. So for x is equal to -2, I'm going to look at the one-sided limits, right? So the limit of f, as I mean, this is going to end up being limit of f plus limit of g, right? So I'll do the limit of f from the left plus the limit of g approaching -2 from the left, right? So we can see that f approaches 1 and g approaches 3, right? So it's 1 plus 3 or 4. This is part A. If I do the right, then I get that f is going to approach, let's see, it's approaching 3 and g is approaching 1. So I get 4 from both sides. So this overall limit does exist and it's equal to 4. Let's do B. In B, x is approaching 1. So again, I have to do the one-sided limits. So for my one-sided limits here, let's start with f plus g from the left. So the limit of f as x approaches 1 from the left plus the limit of g as x approaches, let me just say g, as x approaches 1 from the left. So this is equal to, from the left, f is approaching 1 means y is approaching 2. And then in this one, at x is equal to 1, I'm approaching 0 on g. So this is equal to 2. And from the right side, well, g is still approaching, it looks like 0, right? Because whether I approach from the right or the left, g approaches 0. But f, if I'm approaching from the right side, f now is approaching -1. So this is equal to -1. So the two-sided limits are different, and so the overall limit is a d and e. Okay, the last one is exactly the same arrow number, but I'm multiplying. So I just have to do what I did in the last part B, except I'm multiplying the two limits instead of adding. And so I'm going to get 0 times, or 2 times 0, right, which is 0, approaching from the left. And then from the right, let's see, from the right, it's going to be negative 1 times 0, which is also 0, right? So that means that the overall limit is 0. Okay, so a lot of one-sided things to keep track of when we work with piecewise functions. Okay, we're done. Takeaways, big ones are that the limit laws, first of all, the limit laws themselves are a takeaway, but I didn't want to list them all again. But go over those, remember those, and remember that they work when the individual limits at the arrow number exist. For piecewise function limits, look at the one-sided limits at the boundaries. And if individual limits do not exist due to a jump, which is exactly what happens in a piecewise function, then again, we're going to work with the one-sided limits. Okay, hope you enjoyed limit laws and piecewise functions, and we will see you soon.